Welcome everyone to the fifth webinar hosted by the Data Science Across Discipline Research Group. Today's presentation will be given by Sid Mishra, who is a professor of computational applied mathematics at ETH Zurich in Switzerland. He's also the director of computational science Zurich and an associate faculty member at the ETH Artificial Intelligence Center. He received his doctorate in mathematics in 2005 from the Indian Institute of Science and Tata Institute of Fundamental Research, Bangalore, India. And his research interests are numerical analysis, scientific computing, nonlinear PDEs, computational fluid and plasma dynamics, as well as computational geosciences and machine learning. Welcome, Prof. It's very nice to have you there, and we very much look forward to your presentation. Thank you.
Thank you so much, Karis. So thank you very much for the introduction as well as for the invitation. It's my pleasure to talk to you this morning. I'm going to talk about machine learning, and I'm going to talk about it in a very specific context, which is the context of computations of partial differential equations. So let us start with what are partial differential equations. As many of you might know, tons of physical phenomena ranging all the way from the scale of the atom to the scale of the universe and everything in between, whether it's the Earth's climate or whether it's the growth of a fly wing. All these and many, many more phenomena that are described by partial differential equations, mathematical entities that describes physical phenomena, and we have a whole host of them. So for instance, here you have the Schrodinger's equation that describes the motion of or the description of atoms and molecules, and you have things like the magneto-hydrodynamic equations and the Einstein equations that describe, for instance, cosmology. And as we know, many of these equations, or all of them practically, you cannot write down a formula. You cannot write down an explicit solution formula. So you have to simulate them on a computer. And to that end, we need to take recourse to numerical methods. And there are whole hosts of them. Many of you might have seen them before. So you have finite difference methods, finite element methods, finite volume methods, collocation methods, and so on. Quite a few of them. These are very well established, very successful, and used in different contexts. However, there are many, many problems where these fail or they are inadequate. They do not suffice. And one particular class of problems that I'm going to focus on for this talk are when the PDE has high dimensions. By high dimensions, I mean that the dimensions of the PDE are bigger than 4 because space-time is 4-dimensional. So anything more than that would be high-dimensional. And in fact, you can classify these high-dimensional PDEs into two categories. First is if the high dimensionality is explicit, in the sense that the spatial dimension itself is higher than 4 or greater than or equal to 4. And there are a bunch of PDEs. There was already a question, I think. This was, anyway, there's a bunch of PDEs that have this structure. For instance, in physics, you have the Boltzmann equation, which is 7-dimensional. You have radiative transfer equations. This is what we're going to talk about in a bit. Also 7-dimensional. And then you have Black-Scholes equations, Schrodinger's equations. These can be in tens of dimensions, hundreds or thousands of dimensions. So these kind of PDEs are called explicitly high-dimensional PDEs. And I will address them in the second part of my talk. But in the first part of my talk, I'm going to focus on something called implicitly high-dimensional PDEs. These are what are called parametric PDEs. And let me start with an example, just in case you have not heard of this. So here's an example. This example comes from what is called uncertainty quantification. So a bulk of my research program is on computations of fluid flows. So here's an example of a computation from my group. So you have a turbulent compressible flow. Here is a visualization, a realization of this. So this is the density of a gas flowing in a pipe, for instance, or flowing in a jet. And then the point is that this simulation, you don't need to know the details. It's a simulation of compressible flow. It's a very high resolution simulation. As you can see, it has essentially 1,000 cubed. So something like 10 to the power 10 billion degrees of freedom. And to compute these, you need to access some of the most powerful supercomputers on Earth. And the one that I access is the local one here in Switzerland, which is called DaNT, based DaNT. It is the 12th most powerful or the 12th fastest computer in some sense. And even on this, for a single simulation, it requires 280 node hours. But the point is, people doing engineering are not interested only in this single realization of the flow because it's chaotic. A slight change is going to lead to something completely different. So what you're interested in are computations of statistics, things like the mean, the variance, probability distributions, and so on. And to compute this, a single simulation does not suffice, 10 simulations does not suffice. What you need to have hundreds of simulations, or thousands of simulations. Remember that each simulation is expensive, and when you take hundreds or thousands of them, it's extremely expensive. In fact, one can, in fact, put a price on it because this is Switzerland. People have a price for everything. So if you put $1 or a Swiss franc cost on it, the ensemble simulation for which I can generate the mean and the variance, this costs something like $700,000 US dollars. So you can imagine a single simulation, a single ensemble simulation is that expensive. And all over the world in supercomputing centers, people do these kind of simulations more or less on a routine basis, which tells you how expensive this whole process is. The key point here is a single simulation is expensive, but it's hundreds of thousands of them that makes it very expensive. And another example of this is when you do shape optimization or optimal design. So a typical example of this is when you want to design an aircraft body or airframe, or let's say even the shape of a wing, a cross-section of a wing, the so-called airfoil. You want to design it to, for instance, minimize drag at constant lift or something like that. And again, because it's an optimization problem in the optimization loop, you need hundreds of or thousands of forward simulations of the PDE. So each simulation is expensive, but when you do hundreds of thousands of them, it's prohibitively expensive. And these class of problems where you need to call a PDE solver again and again and again, these are what are called many query problems, right? So I gave you two examples of this: uncertainty quantification, optimal design. And the whole point here is that these are very expensive simulations. And even on state-of-the-art high-performance computing systems, it's quite challenging to do them. So what do we do in that case, right? And what we do is, first of all, we do a little bit of abstraction, and we express these PDEs in a parametric form. Because remember that uncertainty quantification, you have some uncertainty. So you have to describe this initial uncertainty, for instance, by some parameters. And here, for instance, the shape has to be described by some parameters. These are called Higgs-Henne functions. These are some spline type functions. Details are not important. And ultimately, what you end up is a PDE like this. So this is a differential operator. You can think of it as a Laplace's operator, heat equation, whatever, Navier-Stokes, whatever is your favorite PDE. And it's a function of space, which could be three-dimensional. It's a function of time. It's also a function of parameters, for instance, which describe the probability space or which describe the design space. And these parameters can be tens of them or hundreds of them. And this is where this high dimensionality comes in. And remember that what we're interested in is for different values of this y, we have to find either the solution fields, for instance, the whole field around this flow field, around this shape, or in many cases, we're just interested in observable, a quantity of interest, something like the lift or the drag. So these are the objects of your computation. And as I've said before, this is a very expensive process. So what we're going to do in this talk, and this is a research activity happening in different parts of the world, is they're going to approximate the solution fields or these observables with deep neural networks. So this is where deep learning or machine learning comes in. So what we're going to do is we're going to see how deep learning can make the computational cost go down significantly. But how do we do it? And before that, what is deep learning, right? So many of you know this, so it will be a very quick recap. So these days, artificial intelligence, machine learning in particular, is used for everything from machine translation to face recognition to self-driving cars to recommender systems and many, many more things. And the sort of workhorse of this kind of machine learning or artificial intelligence are deep neural networks. So for the purposes of my talk, artificial neural networks are simply going to be functions. So functions means they start with an input. It could be a vector, a very high dimensional vector, and it produces an output, which could be a vector or it could be a number, depending on the context. And the structure of the function is that it's a composition. So starting with a vector, you compose it with an affine function. So this is just an affine function here. And then you compose it with what is called a scalar activation function and nonlinearity, component-wise or entry-wise. And you keep on doing it. So scalar nonlinearity, then you again go to an affine function, scalar nonlinearity, go to affine function, and so on. And you keep on composing it. So it sort of replicates what's happening with neural networks in our brain, because these are feed-forward networks. You start with an input, and you put it into a fully connected layer activation, fully connected layer activation, and so on, and you get an output. So composition is the key here. And the point is, okay, this is a very special structure of a function. How can we represent so many other functions with this structure? The point is that there are degrees of freedom here, because when you take this affine functions, so you have matrices here, which are called weight matrices, and vectors here, these are called bias vectors. Now, these are degrees of freedom. These are, let's say, something that we can fine tune, we can determine. And these parameters, they're determined by training the neural network. So what you do is, remember that my objective is to learn or to approximate this function L by a neural network. So what I do is, I might not have access to the function L everywhere in the domain that I'm interested, but at least I need some data. So you take independent random variables, randomly distributed, some n points, let's say hundreds or thousands of these points, and you say that there is a mismatch between the output of your neural network and this function here. This provides what is called a loss function, and you find the neural network that is going to fit this loss function as well as you can. So this is as simple as that. You have a certain structure for the neural network, you have been given some data, possibly noisy, you don't know that. And then all that you have to do is to find the neural network that is the best fit by minimizing this problem. It's easier said than done, because this is a non-convex optimization problem. Remember that it's a problem, the loss function is a function of theta. The parameters is very high dimensional. Already you'll see tens of thousands of dimensions, hundreds of thousands of dimensions, maybe 1 million dimensions. So this is a very non-convex optimization problem, and you need some sort of stochastic gradient method to solve it. So this is fairly straightforward machine learning 101. And what we are going to do is to take this fairly straightforward machine learning and apply it in our context, which is to learn the fields and the observables corresponding to parametric PDEs. So these are functions. We can get data either by numerical simulations or by measurements. And what we're going to do is we're going to find neural networks which are going to fit this data well. This is a simple objective. Now the question is, can we do that, right? Can we find a neural network such that given my underlying function, solution of a PDE or an observable of a PDE, it is approximated to high accuracy? And the answer to this is in principle, yes, because deep neural networks, and this is what makes them powerful, have what is called a universal approximation property. What does that mean? That means that as long as your underlying function is continuous or even measurable, so it could be discontinuous, you always have a neural network which is going to approximate it. This is something that is well known. And when you look into the weeds, you get a very precise quantification of the error, because you're going to make an error, and the very precise quantification of the error is given here. So there'll always be a neural network, provided that your map has certain regularity. Let's say that it is S derivatives, then it's smooth enough. Then this is going to be the rate. So it depends on the dimension, because remember that these are functions. So this vector here, input dimension, has a certain input dimension. And then you look at the rate here. So it depends on the smoothness of your underlying function, and it depends on the dimension. More smooth the function is, the better approximation you get. More number of dimensions you have, the more high dimensional the space is, worse approximation you get. So this is the sort of the ballpark. Now, the point is, in the problems that I showed you with shocks and with turbulence and so on, this is not very regular. The function is not very regular. You cannot expect a lot of derivatives, and the number of dimensions can be very high. Just to put things in perspective, even in this fairly simple problem, two-dimensional physical space, the number of parameters here is 20 dimensions. But let's keep it even simple. Let's put it only 6 dimensions in the parameter space. The function itself might have only one derivative, in a weak sense, because you can see that there are shocks here. So if you put in the numbers here, what you get out is something not so nice, right? So what you see is, to get 1% error, if I plug in the numbers, I get that my network size is like 1 trillion. And this is insane, right? You're not going to have such huge neural networks. Even the biggest neural networks known today are of the order of hundreds of billions. And for such a small problem, you're not going to use trillions. And the reason why this happens is because we're hit by what is called the curse of dimensionality, because the size of the neural network grows exponentially in the dimensions of your problem. So this is a big constraint. So a priori, it seems as if machine learning cannot work for the problems that we are looking at any more than it should work for the problems that people look at in image processing and speech recognition and so on. However, one needs to do a little bit more fine analysis. Maybe this is the most detailed slide I have. So remember that we have this error, the difference between your ground truth, the function that you want to learn, and the neural network, and you can express this difference in the following manner. You decompose it into three components, and let me walk you through all the three components. The first component is what is called an approximation error. This is just a best approximation. Remember that neural networks are a function space or a function class, hypothesis space, as they call in computer science, and it just tells you what is the best you can do, approximating a general function by this particular class of functions. And remember that here, when we use this, just saying that, okay, these are S derivatives, then we got something very bad. However, remember that we have PDEs, and solutions of PDEs have some special structure. And because of that, we can almost always prove, this has to be done on a case-by-case basis, but one can rigorously prove that it does not depend exponentially on the dimension, because this was what killed us here, right? It was a curse of dimensionality. However, and there's a variety of PDEs for elliptic PDEs, parabolic PDEs, hyperbolic PDEs. One can prove that at worst it grows polynomially. Many times it's just linear or quadratic. So it's not as bleak as it seems. It's much more positive. So the best approximation error tells you that there is a lot of structure that we can, let's say, use or exploit in order to make this problem tractable. Then there's something called optimization error. Remember that in practice, I always have to train my neural network by some stochastic gradient method. And this error is notoriously hard to get estimates on. What you do instead is you just train and you see how much of error do you make, because this is computable. It's your training error. This is a training error. It's a computable quantity. So you know how big or small it is. So that leaves a final thing, which is called generalization error, which is because this is an integral. If you look at this, it's an integral. We're replacing it with a quadrature. So there has to be some error between them. So this is in statistical learning theory. This is called the population risk, and this is called the empirical risk. And the difference between them can be quantified. There are varieties of ways to quantify it. One way is to just use some version of Monte Carlo. Remember that these are random points. So what you obtain here is, what you obtain here is that your generalization error, this error, the difference quadrature error, let's say, it behaves like essentially square root of the number of samples that you have. Okay, there's a logarithmic correction, but this is the detail. So now let's put all these together. So because of the structure of PDEs, we say that this error, the approximation error, can be made small. If it could happen that we have very small training errors. So all that you're left with is error, which behaves something like this. So it depends on the size of your neural network, which let's say is reasonably small. And it depends on the number of samples that you have, training samples, which behaves like a square root here. Okay. Now let's try to do the same process and say that we need 1% error and a simple addition. And let's say that this is of order 1. So what you need are 10,000 training samples. Okay. Doesn't seem so bad. However, this is precisely the challenge that we have. Let's go back to the slides here. So 10,000 training samples, right? Just imagine that each of my samples itself is costing me 300 node hours, and to take 10,000 of this is just infeasible. Similarly, even here, each sample takes about 30 minutes. Still, 10,000 is a very, very large number. The computational costs are going to be humongous. So if I just was limited by this kind of a rough analysis, then again, this is a very, very difficult problem to solve. Because the challenge here is that we have to learn maps of low regularity, fairly complex maps, in a data poor regime, because our data is not generated by taking a picture or listening to a sound, recording a sound. It is generated by either very expensive measurements, experiments, or by simulations, which are also expensive. And this is a big contrast between in classical machine learning and computer science. You have big data. Here, we don't have so much of big data. We have small data, and still we have to somehow use this, right? Can we exploit this? And it turns out that we can, but we have to use a lot of tricks. And the first trick that I can tell you here is that Because we're doing simulations, we're not restricted, or we're not compelled to use random points. We can use other kinds of training points. So remember that random points, they're just distributed randomly. So here the blue points are random points. And as you can see, this is just a unit square in 2 dimensions. And there are many of these small boxes where there are no random points. Okay, so you don't have a lot of information spread evenly. Of course, if I would have taken grid points, then it would have been spread evenly. However, doing it in 100 dimensions is not feasible, or 20 dimensions, or even 10 dimensions is not feasible. So I need something in between, which is well distributed or equidistributed. And there are such points or such sequences. They're called low discrepancy sequences. They are the basis of what is called quasi-Monte Carlo integration. There are a variety of these. These are very easily available. You can generate them. And as you can see, just intuitively, they're better spread out. So for instance, the orange points, the orange stars, are much better spread out in the domain than the blue points, right? So this is the basic intuition, and one can prove rigorous estimates. So ultimately what one proves is, for instance, a result like this, which tells you that the total error is given in terms of the training error. This is something that's always there. And there is a logarithmic factor here, correction here, but essentially it's 1 over n. So remember that here, it was 1 over square root of n, so I needed 10,000 samples. If it's linear, on the other hand, I need 100 samples. And it's, there's a huge difference between having 10,000 data points or generating 10,000 data points and just having 100 data points. So this is very, very useful. And in fact, you can do even better. And you can see that already in practice. So here's an example where the Monte Carlo was doing a little better than a half. It was 0.65. Whereas the Sobol points, this low discrepancy sequences, as predicted, they gave you a rate of 1. And this was a 10-dimensional or 9-dimensional problem. And there's a big difference, right? You have 2 orders of magnitude speed up in your results. And if you have more structure, for instance, if you have elliptic equations, Laplace's equation, parabolic equations, like the heat equation, then this map here can be holomorphic. And there you can do even better. You can have quadratic decay. Of course, there is still this logarithmic correction here. Here, there is no logarithmic correction. So you can, for elliptic and parabolic equations, this is a very tractable problem. But up to 20 dimensions is fine. There's a log, so it kicks on at some point. Up to 20 dimensions is fine. There are other tricks. Maybe I just sort of skip it. I have many things to cover. So there are other tricks that you can use to make this a tractable problem. But the most important trick that we use is, instead of using random points, we use these points with special structures. So let me give you some examples. So here's an example where I'm going to do prediction. Prediction means, let me explain to you what it is. So remember that I have this airfoil here. This is just a cross section of a wing. And I'm going to describe it by a few parameters, in this case, 20 parameters. Okay. And then the point is, I change the shape of the airfoil with these 20 parameters. I think I had a picture somewhere. Maybe it, so sorry about this. I should have, yeah. So as you can see, this is my reference airfoil. And there's a design envelope. So within this, all these shapes are realizable by these 20 parameters. And during the design process, I want to find the best shape that is going to minimize drag, for instance. However, to do this, for any given shape, that is for any given value of these 20 parameters, I have to predict what is going to be the lift and the drag and what is going to be the solution field. And this is exactly what I'm going to do here in this picture. So remember that to generate a single sample, this is a high resolution simulation, it takes about 40 minutes. 40 minutes here. Now we are going to train neural networks. These neural networks are rather small. They have about 1,000 to 10,000 parameters, and it's always with 128 training samples. So it's not a lot of samples. Remember, this is the key point here. So just to get the lift and the drag, it takes me about 15 minutes to train. To get the whole solution field, the whole flow field takes about an hour, which is what it is. This is an offline cost. You can't avoid it. But now look at these numbers here, the evaluation cost. Remember that for each shape, you generate a flow field and you find the lift and the drag. So these are done at very, very fast speeds, right? This is 10 to the power minus 5. The flow field takes a little longer because you have to predict values all over the place. And still it is sub-seconds. It's like 0.1 of a second compared to 40 minutes. So you can imagine that this is 3 orders of magnitude faster, and the errors are between 1 and 2%. So any engineer will take it that you save 3 or 4 orders of magnitude on time, and you have 1% or 2% error. So this is and this was only made possible because of these innovations that I just talked about. So this is one place where you can make very fast predictions using your networks, provided that you make this kind of innovations. Here's another example, uncertainty quantification. You're not just interested in one particular realization of the flow field, you're interested in the statistics. So for instance, here you're interested in the lift distribution, the PDF of the lift, and the PDF of the drag. For this kind of transonic flow, there's a lot of small drags, and there are some places with big shocks where there are large drags. So you have this kind of a distribution here. The lift has this kind of a distribution. And we use the deep neural network as a surrogate, as a replacement for your PDE solver. And we could generate this very accurate distributions. This is again 1% error measured in the right norms. And you can see always it's 128 training samples. And if you compare with Monte Carlo, the classical Monte Carlo method, then you get almost a factor of 250 or 180 speed up. Even with the state-of-the-art method for this, which is quasi-Monte Carlo, you get about 7 to 9. And if you had another trick, which is multi-level training that I skipped, you get something like a factor of 30, which is nothing to laugh about. It's a huge cost in terms of costs. So you can deploy this for uncertainty quantification. You can also deploy this for shape optimization. Again, you have to do a little bit more work because shape optimization is, you're not just interested in the value all over the place, you're interested in optima, right? And these optima are often distributed along a submanifold. And so we propose some sort of an active learning algorithm. It's I don't have the time to go into details, but the idea is that instead of just taking points which are all over the place, either snowball points or random points, what you do is that you iterate between optimization and neural network training, and you try to capture points which are close to this optimal manifold and improve the neural network as a consequence. And the main point is you want to represent the extrema. And this has been, for instance, done in this paper here. And you can see the result of that. So you can optimize the shape. So this was a reference shape. These two shapes are optimal shapes, 2 different types of optimal shapes. And both of them provide you with a 50% reduction in drag, which is a serious reduction. There is a question for later. Minimums of permutations. Yes, I can answer it later. Okay, I can certainly answer it later. Thank you for asking this question. But so the first point here is that this is significantly lower than the drag that you originally started out with. But the main point here is that a traditional optimization method will also find it. So the difference is in the cost. And the cost here is, this is the traditional optimization method in orange. The neural network algorithm is in blue. And you can see already with something between 64 and 128 simulations. Someone has raised a hand, so I can take the question. Yes, please go ahead.
Okay. Dr. Mishra, what I want to ask is, when you talk about this airfoil, I just want to confirm it because when I did physics at honors level, I learned about this aerodynamics. So yes. I just want to confirm whether it has connection to that aerodynamics.
Of course.
It's actually taking me back to that. So may you please give a clarification on that?
For sure. Means this is aerodynamics. It's a flow. I'm sorry. Somehow I'm sorry. Yeah. Okay. Where is the flow? Yeah. This is aerodynamics, right? So you have an obstacle, in this case, an airfoil, and you have a flow which is coming towards it. Or let's imagine the other way around, that this is moving and the air is still. So you have some flow around it, and this is how the flow is distributed. These are the Mach contours. So this is the ratio between the flow field and the speed of sound in air. And as you can see that there is a difference in airspeed, which is why you have this kind of a shock wave here. So yes, this is indeed aerodynamics. So this is the governing equations and the motion. The point is you cannot predict this motion. You can, of course, qualitatively say that, but to predict it quantitatively is not possible. You can't do it on pen and paper. You have to take recourse to a computer simulation. Does that answer your question?
Yes, sir. It's very much clear. Thank you.
Okay, and there was another question by Luke. Let me just answer it, right? So he said that the evaluation cost is incredibly small. Would it be possible to run millions of permutations on neural network weights and understand the sensitivity or not perfect? Yes, absolutely. This is a good point, Luke. In fact, you do that all the time. When one is doing this kind of simulations, here is an example of sensitivity, right? Because this is the prediction or the distribution of the lift. But I agree that even the weights, small permutations of the weights can give you information. Maybe I address this question further during the Q&A later on. Okay, so as you can see that there is a huge difference in cost. So this was a factor of approximately 30. So in all these applications, these are very close to real world applications. This can be done also in 3D. This is in process, and you can see that there is a gain. So maybe I give you another application, which is a very cool one. This is about predicting tsunamis. We live not far from the Mediterranean, but it can be done in the Indian Ocean. It can be done in the Pacific, in the Atlantic, and so on. So the idea here is that there are tsunamis in the Mediterranean. There are active faults in the Mediterranean. For instance, you can have a tsunami which is set off by an earthquake off the coast of Crete here. And then this is after 2 hours, it hits the coast of Italy and everywhere around. And after 4 hours, this is the structure of the waves. And the question is, at the moment, so this is how it is simulated, okay? So you have something called the shallow water equations that model the motion of this tsunami waves. But remember that the tsunami wave itself was caused by the deformation of the seafloor by an earthquake, right? So one has to describe this. One has to somehow relate the seafloor deformation with the initial conditions. And this is done by a Japanese geoscientist a long time back, Okada. So it's called the Okada model. But the point is it has several parameters. It has like 11 parameters. I'm not going into details here. And for each of these parameters, so whenever an earthquake happens, you register an earthquake, immediately one can read off these parameters from the earthquake waveforms. So you read off these parameters, then you sort of switch on your tsunami simulation code. You need also some uncertainty quantification. And this takes you about 90 minutes, but that's a very bad idea, right? Because the wave itself has already reached southern Italy by 90 minutes. So you really need to reduce the simulation time. One can take, let's say, less accurate simulations, but then you sacrifice accuracy. And at the same time, it's still a factor of 5, 10, 15 minutes. And with uncertainty quantification, it takes longer. So we decided to solve this problem by using machine learning. So to do exactly the same thing, use softball points. But the additional complication now is that we have to learn time series. We just can't learn a static field, but learn time series at different points. So I'm just focusing here on the south coast of Italy, Puglia in this particular case, and parts of Basilicata. And as you can see at these buoy locations, these are different locations that one is interested in. So you have the ground truth, which has been computed by a very accurate simulation. And you have the deep neural network, and this is a function of time. So there's a time series. And based on this time series, people make their tsunami early warnings, okay? And you can see here, for instance, you get almost perfect match. Here also you get a perfect match. These are worst prediction. This is the worst prediction. And even this is very good. As you can see, there's a very complicated time series. You have a big wave coming in, several small dispersive waves, another wave here. And then the deep neural network does a very accurate job of it. And again, this is a sub-second calculation. So the earlier one was of the order of minutes. This is less than seconds. So again, you speed up by 2 orders of magnitude. And this is something that can be made operational, I hope soon. But another example where we're able to use this in a very effective manner. Good. So now I have about 10 minutes or a little bit more than that. And let me focus, change gears a bit, because so far I've spoken about this parametric PDEs. Now I'll focus on a different class of PDEs in high dimensions. And these are explicitly high dimensional PDEs. I gave you examples, radiative transfer, Schrodinger's equation, Black-Scholes, and finance, and many, many other things. And here the problem is that there are no parameters. So here there is exactly one problem with an initial condition and boundary conditions, but you might have hundreds of dimensions, as you will see. And the paradigm of machine learning that I've used so far, something called supervised learning, that may not work in this case. And the reason for that is even to generate a single data point is difficult, if not impossible. So what I'm proposing here is to use a slightly different paradigm, something called unsupervised learning, something called physics-informed neural networks. And let me explain that very quickly, actually. So my objective here is to, I'll give you some examples so you can see it. My objective here is to learn a PDE, or in this case, let's forget parameters. I'm a bit, okay, give me 1 second. For some reason, I don't see my screen properly. Okay, now I do. So you have a PDE, which is given by this differential operator here. D, it's a differential operator. You can think of the Laplacian, you can think of the heat equation and so on, which maps a function space to another function space. Now, the point is that we are going to solve the PDE now is simply to find a function u which satisfies the PDE. Let's say pointwise. So these are smooth solutions. Now, what I'm going to do is to approximate the solution of the PDE by neural network. So this means that my neural network takes as its inputs time, the time at which I'm interested, and the spatial dimensions, and I churn out a number or a vector, which is the solution of the PDE. Now, of course, how do you do that? This is just a deep neural network, right? So to do that, we define or we compute. Remember that the deep neural network is always parameterized by this theta. These are the weights and biases of my deep neural network. So it is parameterized by this theta. So I can compute something called the residual of the PDE. And this is here. So I just plug this neural network into the differential equation, which means I have to take derivatives. I might have to take second derivatives, third derivatives, and so on and so forth. This can all be done very efficiently these days by automatic differentiation. So the point about neural networks or about neural network frameworks is that we can do automatic differentiation, which means that I can compute these residuals very quickly. And remember that if I had an exact solution of the PDE, that at every point this residual will be 0, because that would solve my PDE, right? Because it doesn't solve my PDE, it's called a residual, an error. And this is what I'm going to minimize. But of course, it's defined at different points, so I take an integral, right? So the total residual is what is going to be minimized. And these are the theta that corresponds to the neural network, which is going to approximate my PDE. But of course, who can compute integrals exactly, right? This is always a problem. I need some sort of a quadrature. All of us know about quadratures. It can be Monte Carlo, it can be Gauss rules, whatever. And this provides me with a training or a loss function that I'm going to minimize. And the point is that, okay, so what? This is a very easy algorithm, right? So all that I have to do is I have to define my neural network architecture. I have to compute this residual by automatic differentiation. And then I have to use this loss function. I have to minimize this loss function. And this can be done by 5 lines of code in PyTorch or TensorFlow. So this is very, very efficient or very easy to code. However, why should this work, right? What is the connection between this process and the solution of the PDE? And this is what was explained in this paper from last year, where the main point that we made is that your PDE has to be stable. And what does stability mean? In some sense, means not in the traditional sense, but it has to be stable. Stability means that if I change my inputs, so the inputs are going to be the right-hand side of the PDE, F here, then my outputs, which is a solution of the PDE, changes in a proportionate manner. If I do that, it takes about 2 lines to prove that the whole thing works, because my error, which is the difference between my PIN, physics-informed neural network, and the PDE, is given in terms of the PDE residual, which is approximated by the training error, and there is a quadrature error here. So if you can train, and if you have enough quadrature points, then it proves that you have some control on the error and it can be small. Okay, so this is the basic idea, and it has been done in many, many examples. So for instance, let me give you a very simple example of the heat equation here. And this is, you have to take some points. So for instance, you take random points in this case in your space-time domain. You take some points along the boundary, take some points in the initial line. You form these residuals, just compute the time derivative of this function, compute the Laplacian, can be done very easily by automatic differentiation. Compute the mismatch with the initial data, which is given to you. Compute the mismatch with the boundary conditions, which is also given to you, and then minimize the loss function. Remember, here I don't need any other information whatsoever. I need the initial data, I need the boundary conditions. If you wanted to solve the heat equation with a finite difference method, you would have done exactly the same. So now this is a replacement for your traditional numerical methods by using neural networks. And one can prove that things work. And okay, let me just give you some examples of this high dimensionality. So heat equation is a very simple one, but very close to it are the Black-Scholes equations of option pricing, Heston equations, and there are many, many equations that arise in finance, in computational finance, financial engineering, which have this structure. And you can do that. You can solve these equations even in 100 dimensions to about 1.1%, 2% error. This takes about half an hour on my laptop. So this is a very, very efficient way. You can solve PDEs in hundreds of dimensions without any data, except your initial data and your boundary conditions. So this is a very, very powerful way to solve PDEs. I'm running out of time, so I'll give you a couple of more examples. A very important physical example is radiative transfer. Many things that we see and observe about our universe is through radiation. And these are the equations of radiative transfer. Now it's a PDE in 7 dimensions in the most general case, because there are 3 space dimensions, so you have about 7 dimensions. It's 3 space dimensions, it's angle, it's frequency, and so on. So this is a very complicated PDE. And cutting a long story short, let me give you the results here. So you can apply the pins for this problem. This is a 2-dimensional problem, steady, so no time dependence here. You do a good job at it, and it takes about 60 minutes. You get a very small error, 0.3%. But then you can say 2 dimensions, 60 minutes, I can do it with a finite difference or a finite element code. Yes, that's true. But now let's do the same thing for a 6-dimensional problem. Now a finite element method is not going to work in that well. It's computationally very expensive. However, with only the same amount of training time, you get a 2% error. So this method is practically sort of, let's say, it does not have the curse of dimensionality that affects grid-based methods, which makes it very, very powerful. In addition, it's very, very simple to code. So now there are many other PDEs that you can do, which I skip. Let me just come to the very last slides that I have. So one power of this method's physics-informed neural networks is that they allow for a seamless integration or coupling between data and your PDE. Because remember, this is an example of this. This is a Stokes equation, a steady flow. And what you're given here, this is what is called a unique continuation problem. So you have some measurements. You don't have the boundary conditions for some reason. It could be that it's very difficult to measure along a pipe's boundary or along the walls of your arteries or something like that. And then you have some information in the interior. And using this information and the fact that it's a solution of the Stokes equation, you want to predict the values everywhere. This is an inverse problem because it's not well posed in the traditional sense. And it turns out that you can use pins very effectively for this. So you have your PDE, which is the residuals here, and you have the data. So all that you do is you add this mismatch in the data to your PDEs and just minimize them together. We do that, right? And it takes exactly the same time as a forward problem. So traditionally, you have to solve many, many hundreds of forward problems in order to solve the inverse problem. Here at one shot, you can do that. And in fact, this does it very, very accurately. So with very few points, just 80 squared, you can see that there is practically no difference between your ground truth in this particular case. And the error is about 1.5% for the density, for the velocity. And the pressure, you are not even allowed to measure the pressure. You're only allowed to measure the velocity by some passive tracer, for instance. And even with the pressure, it's only 3% error. So you solve inverse problems with the same accuracy. And the same with traditional inverse problems. For instance, for radiative transfer, you can solve the inverse problem, that is given an absorption or find the absorption coefficient given your something called the incident radiation. Again, it takes a little more than an hour and a half. You solve it to about 1-2%. But the point is you solve it, it's a high dimensional inverse problem, and you solve it in one shot. So this is a big, big strength. I think I'm almost exceeding my time. So I come to my conclusion here. So I spoke about 2 kinds of high dimensional PDEs. One was this parametric PDEs, many query problems. And I showed you that by using some tricks, you can do very well on prediction, on uncertainty quantification, on PDE constraint optimization. And when these are not feasible, you can use pins, physics-informed neural networks. They're very good for high dimensional forward problems as well as for inverse problems. But the main point in a way is, the take home message, at least from my point, is that these are not black box machine learning solvers, right? These are not black box machine learning algorithms. To be able to use this efficiently in this context of solving PDEs, you need significant innovation. And I tried to describe to you a couple of ways in which you can do that. So I think I'll stop here, and I thank you very much for your attention. And let me try to get into grid view. Thank you very much.
Thank you very much, Prof. That was a very, very interesting presentation. I really enjoyed it. Before I ask, I actually do have a question. Before I ask my question, is there anything you'd like to say further on the question that Luke raised?
Yes, absolutely. I wanted to answer that properly. Let me read it. It's sort of difficult to, so incredibly small. Would it be possible to run millions of perturbations on neural network weights and understand the impact of sensitivity on the output prediction? Not perfect, but it makes, yes, absolutely. I mean, you do it as a matter of routine, actually. But there are different ways to do it. Look, one way is that you can do it in some sort of a Bayesian perspective using what is called dropout. It means that there are well-established protocols on how to do it. So you do that all the time. So it's a natural output of your machine learning algorithm. So this is always done.
Yeah, no, I completely agree with that. I think it's one of the things that the algorithms actually naturally lend themselves towards, which is quite exciting. I found it very interesting, the different kinds of examples you gave. So my question, Sid, was actually just in your own experience. I mean, I've noticed this obviously with a variety of different computational methods. But are there certain kinds of PDEs or maybe the geometries that they are functioning according or describing that don't lend themselves well to being solved via machine learning algorithms such as pins, which you introduced here?
Yes, in fact, I skipped over this, right? So pins are good for some things and they're not good for some things. In fact, thanks to your question, I can cover my slide now, right? So excellent. Here's an example where they are not very good at, right? So this is a viscous Burgers equation, which means that your viscosity parameter here can go to 0 and you recover the Burgers equation, which is a prototypical example for shock formation and so on. Right? Here's an example. So you start with the sine wave, smooth initial data, but then you have compression. So because of compression, after a finite time, you get the formation of a shock wave. Now, as long as your viscosity is small, 10 to the power minus 3, which is a very small viscosity, you do a very, very good job at it. You can really see that the pin is able to capture it very accurately. But then the point is, we have some theory which tells you precisely what to expect. So it tells you that the error is a function of some constants, which depends on the gradient on the L infinity norm, on how big the gradient is going to be. Now you can imagine as we compress and compress and compress, the gradient becomes bigger and bigger and bigger till it blows up in the limit. And you can even prove that, right? This is classical, that it blows up like a square root. So it's not expected to work in the limit. And you see that also. You see there very clearly that there's some completely artificial, some nonsense. So this doesn't really work in that case. And you see that with the errors, right? Because as you refine, as you take more and more inviscid problems, take smaller and smaller viscosities, make the shocks sharper and sharper and sharper, you get a blow up in the error. It's 25%, which is essentially useless. For the same equation, there is the other case where it's rarefacting, which means that it is decompressing. So then even if you start with something discontinuous, you can have something which is Lipschitz continuous, smooth, or at least in that sense smooth. And here is an example where the estimate tells you that it should work, and it does work, right? Because you can see that the error remains around 1 to 2%. So as long as you have very sharp gradients and these kind of mechanisms, pins are not going to work. Okay, so for instance, if you have fully turbulent flow where the gradient is going to be very badly behaved, then it is not going to work. So there are some ways to work around, because the point is that pins, they impose things pointwise. You pointwise compute the first derivative, you pointwise compute the second derivative. If the second derivative doesn't exist pointwise, then you're going to make a big error with that, right? And so you need to do something called a weak form of pins. So this is one option. But now your neural network, as well as a test function like in finite elements, both of them are going to be neural networks. So there are two neural networks, and one is minimizing, one is maximizing. And this is what is called adversarial training, generative adversarial networks, GANs. And there you can see that we managed to improve the situation quite a bit by almost to 2.7%. It's not perfect still. Nevertheless, it's order of magnitude better. And in fact, in response to Luke's question, here the sensitivity is exactly what is plotted. So sensitivity with respect to the neural networks. So you can see that there are some sensitivities. There's a little peak here, which we understand that it's trying to resolve a shock and so on. So there are problems where pins are not going to work. But there are many, many problems where they are going to work. But one should know, and this is why the theory is very important. So people are trying them in all kinds of contexts without understanding this theory, and this can lead to errors. Absolutely.
I agree. I think that's where your comment on the black box, use of black box.
Yes, exactly, right. So if you just use it, then you have to know a little bit. Otherwise, it's there's a question in the Q&A. Any work in it feels similar to this. There's a very what about COVID, right? Yeah, Luke, people are using neural networks. In fact, one of my PhD students, I think he has used neural networks to calibrate data for COVID. I personally don't do it because I don't really know much about epidemiology. For sure, people are using it, and I don't know how important it is in this context, because epidemiological models are just ODEs, and they're very fast to solve. And if there's no point in trying to learn a neural network, and if the original solver is taking you less than a second, then there's no point in trying to train a neural network and do it, right? The point with these kind of problems is that it takes hours or hundreds of hours, and then you do save a lot. So I don't know details about it, but for sure people are using it to predict and to find patterns that are hitherto not seen, right?
Yeah, no, I think, Luke, they are not necessarily being used to solve models that describe COVID, because like Prof was saying, those models, there are other solvers for them that are so much simpler to use. But should the models that they're using to describe COVID become complex, like a tsunami problem, then yes, I think it would become relevant.
Absolutely, that's the way to put it.
Yeah, at the moment,
and also
I think
with COVID, the point is you have lots and lots of data, right?
Yeah.
And, so you can use neural networks, actually black box ones, rather effectively.
Yeah.
More data, the better they work. It's always the challenge here is how to make them work with less data. This is essentially in a nutshell, the challenge.
Yeah. Especially because a lot of these models like Prof said, there's limited data because of the measurements that can be taken. So they actually also often reason through deep understanding of the underlying physics. That's
Absolutely.
where these.
So you need to, otherwise you can't just use black boxes.
Definitely not. Colleagues, are there any other questions from the audience?
Someone is saying that they want the slides. I can send you the slides.
Okay, perfect. Just so that the audience knows, actually, we've also recorded this session and it will be available on the DSAD Research Group's website. I'll actually put the link here on the chat. And what I'll do is also when Sid sends me slides, I'll also put a link there for the slides. All right. So I'll put that on the chat here for everybody. All right, since there are no more questions, I'd like to just thank you once more, Prof, for your time and for giving us such a very interesting and cross-disciplinary presentation. Also just want to remind our audience that our next presentation will be on predictive maintenance by Dr. Marco Rossi, who's an EDU custom success engineer at MathsWorks, and we look forward to seeing you all there. Thank you, Prof.
Okay, thank you so much, Karis, for the invitation and also for your patience. Okay,
it's
bye-bye. Have a nice vacation.
Bye.
Bye.
The University of Johannesburg, the future reimagined.